What I am going to try to explain in this lecture is how the notion of homotopies and the notion of lifting of paths comes into the picture when we look at covering spaces. Okay. So let me recall that there were two examples of covering spaces of Riemann surfaces that I gave you. One was so let me write that here. One was we had omega, a complex number, non-zero, and then we had the covering map C to C modulo the group, which is the translation by integer multiples of omega. Okay. And I told you that if we call this map as pi sub omega, I told you that this is a covering map and this quotient is topologically a cylinder, and it acquires a Riemann surface structure such that this map becomes holomorphic. And then I told you that if you take a point in the cylinder and take the inverse image, then the inverse image turns out to be set theoretically the same as this group of translations by integer multiples of omega, which also is isomorphic to Z, which turns out to be the fundamental group of the cylinder. Okay. So what I wanted to say was that when you take this covering space situation, the fiber over a point, that is the inverse image of a point, is set theoretically the same as the fundamental group of the base space. Okay. And similarly so pi omega inverse, let me write that down, pi omega inverse, the inverse image of a point x is isomorphic to Z, and which is also isomorphic to the first fundamental group of if I call this as script C sub omega. This is the cylinder with a Riemann surface structure given in this way. Okay. So this is pi 1 of C sub omega. Okay. So of course this isomorphism is an isomorphism as a bijection as sets, and in fact this is an isomorphism of groups. Okay. Because the first fundamental group is Z, and this also turns out to be, so let me write that down, this is bijection of sets, and this is isomorphism of groups. Okay. And in fact what I want to say is that this of course isomorphic also to this Z dot T sub omega. So this was the group this was the group of automorphisms of C, a subgroup of automorphisms of C, which you had to go modulo to get the Riemann surface structure on the cylinder. Okay. So you see the fundamental group of the cylinder is occurring in three ways. You can see it occur in the covering space. This is the universal covering space because you see the top space is simply connected. Okay. So you see the fundamental group appearing in three ways. One thing is it is bijective to the fundamental group of the base is bijective to every fiber. Okay, that is this statement. Okay, the fundamental group of the base is also isomorphic to a subgroup of automorphisms of the covering space, of the universal covering space, and that subgroup is precisely the subgroup modulo which you have to go to get the base below, the base space below. You see. So you see this is how the fundamental, so this tells you two things. First thing is the fiber being identified with the fundamental group is one point. The other point is the fundamental group below being realized as a subgroup of holomorphic automorphisms of the space above. Okay, these are two aspects of covering space theory which are very important that you would like to understand. Okay, so I will try to explain in this lecture how this happens. Okay, so let me also recall the other example. The other example is that of the holomorphic structure on a cylinder, on a torus. Okay, so what did we do? We took two complex numbers, omega 1, omega 2, non-zero complex numbers, and of course we assume that they are linearly independent over R. Okay, so that means omega 1 by omega 2 is not a real number. Okay, that means these two, the vectors represented by these two complex numbers are two linearly independent vectors. They form a parallelogram of non-zero area. Okay, and then I told you that you get a holomorphic structure on the torus in the following way, namely you simply go modulo the group of translations by integral multiples, integer multiples of these two. So it was z dot translation by omega 1 cross z translations by omega 2. Okay, and in this case also the same thing happened. What, namely you take a point x here. Okay, take a point x here, the inverse image by omega 1 comma omega 2 inverse of a point x gave you a grid of points in the complex plane, and the grid was just isomorphic to z cross z, which also turns out to be the fundamental group of this complex torus. Okay, mind you, this is a Riemann surface structure on the real torus S, which is homeomorphic to S1 cross S1. Okay, so I think I call this one can call this T sub omega 1 comma omega 2. Okay, so the fundamental group of the torus is also z cross z. Okay, so this is an isomorphism. So again here we have a similar situation, namely this is isomorphic to the first fundamental group of the torus. Of course I can, whenever I say first fundamental group, it is just first fundamental group as a topological space. I can forget the Riemann surface structure, mind you, because first fundamental group is defined only on the underlying topological space. Okay, and well, again as in this case you see that this is a bijection of sets and well, this is an isomorphism of groups, and in fact this is isomorphic to z dot this subgroup. Okay, so again it is the same picture. This is again a holomorphic universal covering. Okay, for every point here the inverse image is isomorphic to the fundamental group below as a set. Okay, and the fundamental group of the base can be realized as exactly a certain subgroup, namely this one, subgroup of automorphisms, holomorphic automorphisms of C of the universal covering space, modulo which you have to go to get this holomorphic structure on the torus. Okay, so these are two nice examples and they tell you what happens in general. So one would like to understand the following questions. First of all, why is it that the fundamental group of the base shows up set theoretically as the fiber over each point? That is the first question to answer or to understand. Okay, the second question is, how is it that the fundamental group of the base how is it that it can be realized as a subgroup of automorphisms of the covering space? Okay, so the key to this understanding is what is called the Covering Homotopy Theorem, okay, which is a fundamental tool in the study of covering spaces, and which is what I'm going to try to explain. Okay, so to begin with, so let me make some definitions So the first definition is following. Okay, so let me make a few blanket assumptions. In the course of our discussion we will need several hypotheses, and so I am going to make some blanket hypotheses about the kind of spaces that we are going to work with. We may not be using all the hypotheses, or maybe we may use some weaker hypotheses in certain cases, but just to make the exposition simple, I will make some blanket assumptions. Assume all topological spaces are well, I think I should erase this. Assume all topological spaces are by that I mean all topological spaces that we are going to talk about. Okay, number 1, Hausdorff, which is essentially that any two distinct points can be separated by disjoint open neighborhoods. Then number 2, arcwise or pathwise connected. Number 3, so of course if you recall, arcwise or pathwise connected means that any two points, any two distinct points can be connected by a continuous image of an interval, okay, a closed interval, and then locally arcwise or pathwise connected. A weaker condition than 2 is just assuming connectedness, okay, which is weaker. So if you assume arcwise or pathwise connected, it implies that it is connected, okay. So a weaker condition for 2 would be connected, and whenever we can assume that I will make a mention of it. Then the fourth one is locally simply connected, locally simply connected, okay. So this is the condition that every point has an open neighborhood which has the property that it is simply connected, namely that any closed path in that neighborhood can be continuously shrunk to a point, okay. So closed path means a continuous image of an interval which starts at one point and ends back at the same point, okay. One sometimes refers to this as a loop based at a point, okay, and the condition for simply connectedness is that this loop can be continuously shrunk to 0, and that can happen only if there are no holes in that neighborhood, okay. So we put all these conditions, okay, in what follows, okay. So I will make the first definition. The first definition I want to tell you about is that of a local homeomorphism, okay. So a continuous map f from let me say y to or let me just put x to y is called a local homeomorphism if for every point x in X there exists an open set V, let me call it as U, there exists an open set U in X, X belonging to U such that F restricted to U from U to F of U is a homeomorphism onto an open subset f of u of y, okay. So the definition of a local homeomorphism is a continuous map such that at every point I am able to find a neighborhood which this map maps homeomorphically onto an open neighborhood in the target topological space, okay. So so the what is a connection? You know that every covering map in fact these covering maps, if you remember, I explained that they are all open, okay, because you take any set here, okay, then its inverse image is just translates of a fixed copy of this set above, okay, and all these translates are disjoint. If you choose a set below small enough, they will all be disjoint. If you choose a set, if you don't choose them small enough, they will still be a union of open sets, okay, and the quotient topology will tell you that you know, a set here is open if and only if the inverse image is open, okay. So if I start with an open set here, I take its image there, okay, then you can check that this is an open then this is an open set here, okay, and why is it an open set? That's precisely because of the quotient topology, because its inverse image will be all translates of the original open set I started with here by this group, and all these translates are all open, okay. So that is the reason why the image of an open set is open. The same thing happens here. So let me repeat that. Why are these open maps? Because I start with an open set here, I take its image there, I want to say that that is open, but by the quotient topology this is open if and only if the inverse image of that is open. But what is the inverse image? The inverse image is just translates of the original open set I started with, translates by these maps, okay, the union of all such translates, and each such translate is an open set, and therefore the inverse image is the union of all such open sets which are translates, and therefore it is open, and therefore this is an open map, and this happens in general for a covering space, okay. So what I wanted to say is that and of course you know a covering space has this property, the property of being a local homeomorphism, okay, because a covering space definition is you give me a point, every point below has a neighborhood such that the inverse image is a disjoint union of neighborhoods, each of which is homeomorphic to the point to the neighborhood below, the admissible neighborhood below. So if you look at it, that it will tell you that every covering space is in fact a surjective local homeomorphism, okay. So so example, every covering space I should say every covering map is surjective local homeomorphism, okay. So this is an example, and but of course the covering map is more, just it's not just a surjective local homeomorphism, but it's more than that. But why did I single this out? Because of the following fact, namely you take a surjective local homeomorphism, okay, then it will be an open map, okay. So so lemma, a surjective local homeomorphism is an open map, okay. So this is very easy to prove, you can convince yourself of this, and as a result what it tells you is that every covering map is also an open map, and of course by open mapping you mean a map which maps open sets to open sets, and that is what is happening in these cases, okay. So what is happening in these cases is also true generally. A covering map is always an open mapping, it takes open sets to open sets, okay, and the reason is because it is a surjective local homeomorphism, okay. So in particular any covering map is open, okay. So this is a very simple exercise in topology, you can check it. Now having said this, the next thing that I would like to worry about is I would like to talk about the converse condition. Okay, so suppose I know that I have a surjective local homeomorphism, okay, which is of course true for a covering map. Okay, what more conditions do I have to put to a surjective local homeomorphism so that it becomes a covering map? Okay, so the surjective local homeomorphism is a weaker condition than a covering map. Okay, so my question is, can you put some more conditions to this so that you can get back the covering property, okay, the property of a covering map. So this is where the lifting property, the unique lifting, the lifting property of maps comes into the picture. Okay, so I'll explain what that is. So maybe I can use, I'll draw this line here and remove this. So let me talk about next let me talk about liftings of maps. So the situation is the following. You see, I have a map f from x to y, which I am purposely writing it vertically. Okay, and suppose I have a map from z to y. Let me call this as h. Okay, so given so let me say that given continuous maps h f from x to y, h from z to y. Okay, so these are continuous maps. A lifting of h to x is a map h tilde from z to x such that h tilde followed by f is h. So this is a lifting of a map. So there is a h tilde. Of course, when I say map, I mean of course continuous map. Okay, we are in the category of topological spaces. So so if you want, I should include here continuous. I'll just put CTS. Okay, so what has happened is that this map h has been lifted to a map h tilde. And why do we call this a lift? Because this followed by this is this, that is this condition. Okay, so we say that h tilde is a lift of the map h. Okay, h tilde is a lift of the map h. Now there is a very nice lemma. The lemma says that, you know, if you have a surjective local homeomorphism, suppose this map f is a surjective local homeomorphism, and suppose this set z is say connected, okay, and locally connected, okay, which is slightly weaker than arcwise connected and locally arcwise connected. Okay, so in that case there is something very nice that's going to happen. It says that if you have two liftings, suppose you have two liftings, and suppose both liftings coincide at one point of z, then they coincide everywhere. Okay, so the moral of the story is, if you have a lifting, okay, with a prescribed value at a point of z, okay, then that is unique. Namely, if there are two liftings which have the same value at one point of z, then they have to be everywhere equal. Okay, so this property is called the uniqueness of lifting property. Okay, and this uniqueness of lifting property happens whenever f is a surjective local homeomorphism. Okay, so let me state that we say f has the uniqueness of lifting property if whenever there are two liftings let me call them h1 tilde h2 tilde of h, okay, such that h1 tilde of z naught is equal to h2 tilde of z naught, okay, then h1 tilde is equal to h2 tilde. So what I am defining is this uniqueness of lifting property. So what is this uniqueness of lifting property? It says that if you have two liftings h1 tilde h2 tilde, namely two maps like this which when composed by f give h, okay, and of course again when I say maps I always mean continuous maps, okay, and suppose these two are going to coincide at one point of z, okay, then they are going to coincide everywhere, right. So the nice thing is that a surjective local homeomorphism is going to have this uniqueness of lifting property, okay, right. So let me write that down. I will just check the let me just check the hypothesis. Maybe if one spends a little bit more time, some of the hypotheses can be weakened, but anyway let us not worry too much about that. So let me state this lemma here. Surjective local homeomorphism has the uniqueness of lifting property, okay. A surjective local homeomorphism has the uniqueness of lifting property, okay. So in other words if f from x to y is a surjective local homeomorphism, okay, then it has the uniqueness of lifting property, namely you give me any map from any other topological space to y. Of course when I say any other topological space I am assuming at least that for example it is connected, and I am assuming all these things. So I may not need all of them to get the conclusion, but for safety I am assuming all of these conditions. So in particular I am assuming z is connected and locally connected, okay. So then any map, if you give me a map from z to y which has two liftings, and if these liftings are same at one point of z, then they have to be same everywhere, okay. So this is in particular true of covering spaces, because covering spaces are of course covering maps are of course surjective local homeomorphisms, okay. So this is in particular true of covering maps. I will tell you why this is important. It is important for the following reason. So you see, suppose from x tilde to x, suppose I had a covering space, okay, and suppose I take I to be the unit interval, and I take a map from I to x. You know the image of I is going to be a path in x, alright. So so if I draw a diagram, then this is my x and I am going to get a path, okay. This path is going to start at alpha of 0 and it is going to end at alpha of 1, right. Now suppose I am able to find so you see, so this point is alpha of 0 and this point is alpha of 1, okay, and there is this covering space above, and let me draw it with a little bit more space so that I can draw it like this. So here is my covering space above, okay. Suppose for this point here, suppose I choose a pre-image above. After all, the covering map is surjective, okay, and you know given any point here I can choose a pre-image, okay. then if I am able to find a lift alpha tilde of this path alpha, it is going to be so this is my path alpha and I am going to get another path here above alpha tilde. The only thing is that this point is alpha tilde of 0, that point is going to be alpha tilde of 1, and under the projection P alpha tilde of 0 will go to alpha of 0 and alpha tilde of 1 is going to go to alpha of 1, okay. And suppose I have a lifting like this, and then this lemma will tell me that the lifting is going to be unique, okay, in the sense that if I had another lift starting at alpha of 0, okay, then I will get starting at alpha tilde of 0, okay, then that is going to give me another lift here and both the lifts coincide at the point 0, okay, alpha tilde of 0 they both coincide here, they coincide at the point 0 here, okay, both maps. So what I am trying to say is that if I really draw it, you can imagine such a situation, namely that I have alpha 1 tilde, I have also alpha 2 tilde, I have two lifts of this map, okay, which of course means that alpha 1 tilde followed by P is alpha, and the same is true of alpha 2 tilde also, okay, two lifts. And suppose that alpha 1 tilde and alpha 2 tilde have the same starting point. So this is alpha 2 tilde of 0, this is the same as so let me write that here, and this is alpha 2 tilde of 1, okay. So this map is alpha 2 tilde, this path is alpha 2 tilde. So you see the path below is alpha and it has been lifted, let us say, to two paths, well, alpha 1 tilde and alpha 2 tilde. So but I have assumed that this starting point is the same, the initial point for both paths is the same. Of course alpha 1 tilde and alpha 2 tilde at 1 they should lie above alpha of 1 because of this condition, these paths lie over this path, so if I follow this path by the projection I should get the path below, okay. So it is clear that alpha 1 tilde of 1 and alpha 2 tilde of 1, the end points are certainly points lying above the end point below, okay. But that is not the point. The point is that this both the maps alpha 1 and alpha 2 they agree at the point 0, that is what it means to say that they start from the same point alpha 1 tilde of 0 is equal to alpha 2 tilde of 0. And what does the uniqueness of lifting property now say? It says that these two paths have to be the same. So the moral of the story is if you have a covering space, okay, like situation, you take a path below, okay, and for this path you take the initial point and choose a point above, okay, then there is a unique, if at all there are paths above that lift to this path, there can be only one, okay. So you see a path below is going to give a unique path above if you fix the initial point above, okay. So you see now you can guess that in some way the fundamental group is going to be involved, because after all the fundamental group is connected with closed paths, okay, and taking homotopy classes. So this is how it enters into the picture. So so then alpha 1 tilde is equal to alpha 2 tilde. So given a path below, if at all you can lift it only to one path provided you fix the initial point above. At this point matters, you could have fixed some other initial point and then you would get some other path, okay, but once you fix the initial point above lying above the initial point below, then there is only one path you can get, okay. So so we say that this uniqueness of path lifting property is true for covering spaces, okay. Now there is another question, look at this definition on the uniqueness of lifting property, okay. Mind you, the uniqueness of lifting property is for any maps, not just paths. I specialize to the case of a path, okay, but it's true, it's supposed to be defined for any maps, alright. You see, we still don't know whether given a map you can actually lift it, okay. For example, what this condition says is if you get two lifts which agree at one point, then they are the same, but it doesn't guarantee you the existence of a lifting, okay, it doesn't guarantee you the existence of a lifting. So where do you get that from? So it happens for covering spaces, okay. So in the case of covering spaces you have the existence of a lifting, okay, and then because it's also a local homeomorphism the lifting is unique, okay. So we say that the covering spaces have the covering maps, they have the unique path lifting property, okay. So so to explain that, let me draw a diagram just to so let me say the following. Covering spaces do have the unique path lifting so what is this unique path lifting property? Unique path lifting property is given a path below you can get a unique path above provided the initial point of the initial point above has been fixed, okay. So it gives you existence of a lifting, and of course uniqueness of a lifting follows from this lemma, okay. So if I draw a diagram, so I have a diagram like this. So I have a covering map. So of course I should actually write covering maps. Let me do that. Of course you know when I say it's a property of a map, of course the source and the target spaces are also involved. So if I say covering space, of course it also involves a covering map, and if I say covering map also it involves the source and target spaces. So sometimes by abuse of language one interchanges this, but anyway, so the point is, you see, you take covering maps, they are surjective local homeomorphisms, which are of course open maps, okay, and surjective local homeomorphisms have this uniqueness of path lifting property, uniqueness of lifting property, of course uniqueness of lifting provided you know the lifting at one point is prescribed, okay. I am not just saying that just take any two liftings they are the same, that is not correct. Two liftings which agree at least one point is what I want, okay. So here also I am not just saying you take a path below there is a unique path above, no, a path below will give you a unique path above provided you fix a starting point which has to be a point you fix lying above this point below, okay. So you have uniqueness of lifting property, and then you have the path lifting property. See, a map can have, any map can have a path lifting property which you can define in a very simple way. A path below can be lifted to a path above, okay. So I can define it for any map, okay. Any map can be said to have a path lifting property if given a path below you can lift it to a path above, okay. So well so what I was trying to say is if you take a covering map you are going to get a uniqueness of lifting property, okay, because of this series of implications, and then I have also told you, I am also telling you here that there is a unique path lifting property, which means that you also have the existence of lifting paths, okay, and these two put together let me put it like this, these two put together give you the unique path lifting property. So this is a property that ensures that given paths, given a path below, you can always lift it to a path above and that path is unique, alright. Of course whenever I say unique path above, the starting point has to be fixed, okay. And the covering maps, they have this path lifting property. How this comes about is by what is called as the covering homotopy theorem. So this is the so I will write it here, covering homotopy theorem. It is the basic tool to link these ideas, okay. And the beautiful thing is I started with this question. You see, a covering map is a surjective local homeomorphism which has a uniqueness of lifting property, okay. And I asked you what more should you add to a surjective local homeomorphism to make it a covering space. The answer is as follows: you take a surjective local homeomorphism which has the path lifting property, okay. Of course if it has a path lifting property, it has to be a unique path lifting property because the surjective local homeomorphism is going to imply uniqueness of lifting. So you add this property of path lifting to surjective local homeomorphism and what you get is a covering map. So it's a very beautiful result. So I'll just signify that by putting a map like this, putting an arrow like this, okay. A surjective local homeomorphism which has the path lifting property, okay, has to be a covering map, okay. So this will tell you in a certain way how covering maps behave, okay. So you can think of a covering map also as a surjective local homeomorphism with the path lifting property. Of course uniqueness of the path lifting, uniqueness will come because it is already a local surjective local homeomorphism, okay. So well, now what remains is somehow to explain the covering homotopy theorem, okay. So let me do that. So let me state the covering homotopy theorem and indicate to you how the inverse image of a point under a covering map is bijective to the fundamental group of the base, okay. So I need to explain that, so I will do that next. So let me write this down, covering homotopy theorem. Okay. So my situation is the following. So this is as you can see, this is a theorem that describes the property of covering maps, okay. And what it tells you is that you can lift homotopies, okay. So let me write on the statement. Let P from x tilde to x be a covering space, okay. Let it be a covering space. Let so I will first draw a diagram so that you can visualize what is happening. So I have x here, I have P, I have I have x tilde, okay, and roughly what I have is so let me think of the following situation. Let us assume that you know there is a path here which starts say a path alpha, and suppose there is another path beta, okay, and let us assume that alpha and beta are homotopic, fixed endpoint homotopic. So so there is a family of paths like this, okay. So this means that so I have a homotopy which is a map f from I cross I to x, okay, such that f of so this I is treated as the let me treat this I as a time parameter, okay, which means that f of x comma t is written as f sub t of x, okay. So and I want f0 of x to be alpha, f1 of x to be beta, okay, and whatever I get in the intermediate paths they will be f sub t's, right. And of course all these paths start at the same point and they end at the same point, and they all end at the same terminal point. So I will put that condition as f t of 0 is, let me say, x naught, and f t of 1 the terminal point is always is say x1, okay. So I have two paths here alpha and beta on x which are homotopic, okay. Now suppose I fix a point above x naught. So I fix a point, let me call this as x naught tilde, that is a point above, okay, and suppose I have a path here which lies over alpha, okay. So I have a path alpha tilde, okay. Then the conclusion of the theorem is that I can lift the whole homotopy to a homotopy of paths above, okay. So I will write that down, and given, so let me write this here, given a homotopy of paths from alpha to beta on x, which is given by this data, and given a lifting of the path alpha to alpha tilde, okay. So let me rub the rest of this pole. And given a lift a lifting alpha tilde of alpha to x tilde, okay. So this is the picture, this alpha tilde followed by p goes to alpha, okay. Then we can find a homotopy G I cross I to x tilde, okay, which is a lifting of f, which is a lifting of f with G0 is equal to alpha tilde, okay, where of course g sub t of x is g of x comma t. So when you put t equal to 0, you get g 0 of x, and g0 of x lies above f0 of x, which is alpha, and g0 of x is g0 is just alpha tilde, okay. So this is so what I have written is actually a special, it's actually a special case of the covering homotopy theorem. So this is not the full covering homotopy theorem. The full covering homotopy theorem is more general. It's not just about lifting of maths, okay, it's not just about lifting of homotopies of paths, it's about lifting of homotopies of maps, and you will have to replace this I here by an Z which is a compact connected space, okay. So let me write that down. So I wrote this particular case because this is a special case of the covering homotopy theorem. So let me write this more generally. Any homotopy so let me write this as f from z cross I to x, okay, with z compact, and of course you know one has to assume z is connected and locally connected. Yeah, I think in this case connected, locally connected, okay. So any homotopy f, okay, can be lifted to a homotopy G. So G, so f is going to be like this. I will be able to lift it to a homotopy G. This is the homotopy, okay. It can be any homotopy, can be lifted to a homotopy, but of course you need to prescribe the value at a point, okay. So I should say with G0 lying over f0, okay. So G0 is just g of x comma 0, okay, and f0 is f of x comma 0. So you see of course when I say it can be lifted to homotopy G with G0 lying over f0, I mean this is understood because G followed by P is f, so Gt will lie over ft, okay, for each t in I, right. So but the point is of course as I told you this being a covering map, this homotopy is a lift of f, okay, and in fact you can choose G in a very special way. The theorem says that the G can be chosen in such a way that you know whenever f is stationary, okay, that is f does not depend on time for a particular value of z, okay, you can choose G also not to depend on time for that particular value of z. So let me write that down. In particular, in fact we can choose G to be stationary whenever f is, okay. What this means is the following, so let me write that down here. that is if Z is a point of Z with f of Z comma t constant in a subinterval of I, okay, then g of Z comma t is also constant for that. Of course, when I say if f z small z belongs to capital Z with f of Z comma t constant in a subinterval of time, which means t should belong to that subinterval for all values of t, for this value of Z and for all values of t in that subinterval, then the lift g will also have the same property, namely g of Z comma t will also be constant for that subinterval. Okay, so f of Z comma t being stationary for a particular value of Z means that for that particular value of Z you vary time, it does not change, and the same property will be true of g also. Okay, so so this is the, you can see that this is the general statement of the covering homotopy theorem. This is a special case, this is a special case that you get when you put Z equal to I. Okay, this is a special case that you get when you put Z equal to I, and now this has beautiful consequences, right, which I will try to explain.